Hello everyone, I apologize for the video format, but I've tried 6 different video softwares and none of them are working, so this is what we're left with. Today I'm going to be talking about the center of gravity and centroids. The center of gravity. This is the point of an object where gravity acts on the body and the distribution of weight is equal in all directions. The center of gravity does not always lie within the mass of the shape. We can use geometry and moment to determine the center of gravity. So in this example down here with the cone, you can see that the center of gravity is 1/4 of the height of the cone and directly in the center of the circle. But if this was a traffic cone, we know that there is an air pocket inside, and that would mean the center of gravity would exist outside of the mass of the shape and rather inside the air pocket. Centroid. For most simple solids, the centroid and the center of gravity are the same. So for this class, we're going to just assume that they're the same. A centroid is the geometric center of an object of uniform density. So in this example down here with the red rectangle, the green dot is the centroid. It's half the base and half the height. If we gave this shape a third dimension in the z-axis, and we find that it's not actually rectangular, it's triangular, then the centroid or center of gravity would shift to where the weight or mass is equal on both sides, or all sides rather. Centroid equation. So we usually denote centroid with the letter C. Sometimes you might see it as G, but typically we use C. The centroid has an X and a Y coordinate, X bar and Y bar. We solve X bar and Y bar separately with the same equation though. X bar is denoted with a little X with a little bar on top, and Y bar is Y with the bar on top. We calculate the centroid of complex shapes by splitting them into smaller, less complicated shapes. So down here at the bottom left right here is our centroid equation. And you can see that centroid is equal to the sum of the number of shapes, which is the area of that shape times the midpoint of that shape divided by the area of that shape. So if we had 3 measurable shapes, we could see the sum of 3 shapes is equal to the area of the first shape times the midpoint of the first shape plus the area of the second shape times the midpoint of the second shape plus the area of the third shape times the midpoint of the third shape divided by the sum of all the areas. This will make more sense when I go over the example problems. Centroid equations. So these are some of our basic equations that are that will make our life a little bit easier. In this class, we're going to really deal with most rectangles and triangles, but we might see some semicircles. The most important one right here for X bar and Y bar equations is for a triangle. The Y bar is the height divided by 3, and the X bar is the base plus the distance from the top vertice to the axis divided by 3. So this is A, this is B, you add them together, divided by 3, and that gives you the X bar. Now for a quarter circle, X bar and Y bar equations are the exact same. That would be a 4 times the radius divided by 3 pi. Now, this is important because if we look at this not as a quarter circle, but as a right triangle, we can also determine the centroid of that by using this Y bar equation up here for the triangle. So the height divided by 3, and if we wanted to do an X bar of a right triangle, it would be the base divided by 3. So example 1. So this shape in the top right here is the one we need to find the centroid of. First things first, we need to pick an origin and write our sign convention. Just write a sign convention for every problem we do in this class. Just stay consistent with it. And I'm going to pick the bottom left corner of this shape as our origin, since that lines up with my coordinate system. We're going to split the shape into easily measurable parts and then number them. So I split it into 3 rectangles, a 4x8, a 2x10, another 2x10, and I labeled them 1, 2, 3. So for X bar, you could start with Y bar, but I started with X bar, it doesn't really matter. we need to find the area of each of these shapes. So 4 by 8 is 34, 2 by 10 is 20, and 2 by 10 is also 20. The midpoint of our first shape in relation to the x-axis is 2 inches. And that is because our object is 4 inches wide and it starts at the origin. So that would mean half of that is 2 inches. We have the midpoint is 2 inches. Our second object, which starts on the y-axis, is 10 inches wide. So half of that would be 5 inches. So the midpoint is 5 inches. Our third object is 2 inches wide, but is 10 inches from the origin. So the midpoint of that would be 11 inches from the origin. And now we're going to plug this into our centroid equation and get the area times the midpoint plus the midpoint times the area plus the area times the midpoint divided by the sum of all the areas. And that gives us x bar, which is 5.24 inches. Y bar is very similar, using the same area because we're using the same shapes. We need to determine the new midpoints. So this is in relation to the y-axis, and our first shape is 8 inches tall. So if we divide that by 2, we have 4 inches. Our second shape is 2 inches tall, but is 8 inches from the origin. So the midpoint would be 9 inches, which is 1/2 of 2, 1 plus 8, 9. And the midpoint of our third shape, which is lined up with the x-axis, would be 5 because it's 10 inches tall and half of that is 5. So we're going to plug that into our centroid equation. We'll get the midpoint times the area plus the midpoint times the area plus the midpoint times the area divided by the sum of the areas. And that gives us y bar, which is 5.62. Example 2. So using moment, where is the center of gravity of this member? Assume the supporting member density and weight is negligible. So if we just kind of set this up as the moments equal to each other, 25 pounds times x1, which is our first distance, equals 100 pounds times x2, which is our second distance. Well, this equation has two variables, x1 and x2. We can see that 100 pounds is 4 times 25 pounds. So using that logic, we can determine that the center of gravity is 4 times closer to the 100-pound block, and vice versa, it'll be 4 times further away from the 25-pound block. If our total distance between the two centroids of our objects is 20 feet, we can divide that into 5 sections, giving 4 of those sections to the 25-pound block and 1 of those sections to the 100-pound block. And that would equal 400 pounds on both sides. You can see these two moment equations both equal 400 pounds. Now, if in this example, the member had its own weight, let's say like 2 pounds per foot, then this would not be the center of gravity. Rather, it would be shifted very, very slightly to the left, because this would be an additional, 32 pounds, and this one would be an additional 8 pounds. But also, shifting our center of gravity is going to change our moments. So we really got to figure that out in a different example. Center of gravity continued. When suspending an object, the force that gravity applies on an object will always pass through the center of gravity. So in this example, I've got 3 pictures. The first one has an evenly distributed load. The force of gravity goes directly through the center of gravity of the load. In the second picture, we have an unevenly distributed load. So the center of gravity is pretty much directly below this block, meaning the force that gravity exerts on this system will go directly through that. So for that to happen, the whole system would rotate, as you can see in the picture, to stay true to that rule of physics. And if we wanted this second picture to be stable, we would have to shorten the length of this left cable so that both moments are equal. The center of gravity point travels in a direct path. While an object may rotate as it falls, the center of gravity will be the axis that the object rotates about. I have a little picture right here of a hatchet that was thrown. The center of gravity, the hatchet, is right below the axe head, and it stays in a direct parabolic arc, while the hatchet itself rotates about that point. And the same thing with this coffee mug. The center of gravity maintains a direct straight path down, while the coffee mug rotates about that center of gravity as it falls down. This is our third example. A barge has a 200 US ton crane on one side and a 310 US ton counterweight on the other side. If the center of gravity of the crane is located 30 meters from the center of gravity of the barge, then how far from the barge's center of gravity should the counterweight be? So in this diagram down here, you can see that we have the 200 US ton crane, 30 meters from the center of gravity of the barge, and the 210 US counterweight that is X distance from the center of gravity of the barge. We can use a moment equation. The sum of moments of the barge equals 310 US tons times X distance minus 200 US tons times 30 meters. 200 times 30 is 6,000. So 6,000 US tons divided by 310 US tons equals our X distance in meters, and that is 19.4 meters. These are my sources. If you have any questions, please let me know. I can try and answer them. Thank you very much for watching. I know this is not the desired media